Hello again, and we're going to go over just another different application of how to use these force versus time graphs. So, yeah, it's basically just some examples. For this, a mouse pushes over a 0.6 kilogram chunk of cheese. So that's the mass of something that we're dealing with. It was initially at rest, right? So that's a initial velocity. The force versus time graph is given below, and just a quick little alert that's meter in milliseconds, right? It's in milliseconds. So the time is in milliseconds. So what is the cheese's speed? So I'm solving for like how fast it's going at the end after this whole 20 milliseconds. Okay. So again, force versus time graph, I'm thinking I can find impulse and relate it to speed with momentum, right? So I'm going to start with the impulse momentum theorem, which says that the impulse on an object is equal to its change in momentum. And just for a refresher, right, this piece is the impulse, and this piece is the change in momentum. That's why we call it the impulse momentum theorem. Okay, so with that, let's get that out of the way. It's in my way now. With that, we go, okay, I'm being asked to figure out what is its speed? Like, how much does it change by throughout this problem? So I'm trying to solve for delta V, change in speed. So I'm going to isolate that variable. And here I have, the impulse divided by the mass. Well, the impulse, force times time, just comes from these axes being multiplied together, which is the area. So over the entire 20 milliseconds is this whole shape, right? And that's just one big triangle. So the area of this triangle is 1/2. The base is 20 milliseconds. Remember, 20 milliseconds. If I have 20 milliseconds there, I would take this decimal and I have to divide by 1,000 to make this into seconds. So I would move the decimal 1, 2, 3 times to make that into seconds, right? So that's 0.02 seconds. And then the height right here you can see is 20 newtons. And when I multiply that stuff together, I end up with 0.2. So 0.2 kilogram meters per second. And if those units seem weird to you, in the previous video, we went over how the units work out. You can check that out on the first example. And then the mass we said was 0.6 kilograms. We'll notice what happens. Right? These kilograms cancel each other out. And so our answer, when we do this, 0.2 divided by 0.6, that could reduce to 1/3 or 0.33. And then our units, we just have meters per second left over. So we have a velocity. So here's the thing, just be careful, right? This is like an alert type thing. This is change in velocity. Like we just solved for change in velocity right there, right? So this is how much the velocity changed by. It was initially at rest. So if the initial velocity is 0, and then we changed by 0.33, that means the final velocity, if it started at 0 and it changed by 0.33, the final velocity, or the final speed, is 0.33 meters per second. Okay? Oh, you're good. What's up?
Hey, I want to give you a heads up.
Yeah. And moving on to the next example. Here we go. All right, let's read through this one. Oh, my God.
License plate BWD3127. Please move your vehicle. It's in a reserved spot.
Really not the best thing for when I'm making a video. Hey! a croquet player hits a zero, I'm talking to the video. Croquet player hits a 0.5 kilogram ball that is initially at rest. So there's the initial velocity. Here is the mass of the ball. The net force is given in this graph, and we want to know the change in momentum. So just remember that is the mass times change in velocity. And it's over after the whole 35 milliseconds. So here's 35 milliseconds right there. Right, so we're going to do everything up to this. And you notice there's like different spots going on. So I'm going to break this up into a couple different shapes. There's a rectangle. And then here's a triangle. And we're going to need to find the area of each one of those. So this right here has a 20 millisecond base, right? So if I do the area of the triangle, that's 1/2 0.02 seconds because it's 20 milliseconds. And then the height is -10. So that gives me an area of, what is it, 1? -0.1. Okay. This area for the rectangle right here is 5 milliseconds. That's the base, so 0.005 seconds. And a height of -10. Which, good morning, would give me -0.05. All right. So when we set this stuff up, remember the impulse momentum theorem, right? This whole thing, mass times change in velocity, that is the change in momentum. So as long as I find the area, we're going to be good. So the area would be adding together both of these things. Right? So -0.15 kilogram meters per second. That is equal to my change in momentum. And that right there is my answer. It's negative, so that means my change in momentum, my momentum decreased over the course of the problem. Okay. Good morning, everybody. Uno más. I'm not talking to myself, I'm making a video. Got a physics student throws a 1 kilogram book, so that's the mass, hits the wall and stops. So if it stops at the end, that's the final velocity of 0. Here we have our graph of force versus time. What is the book's initial speed? So we want to know how fast was it going at the beginning, right? So I'm going to start with my momentum impulse theorem relating, this graph that we have to all this. And I'm trying to figure out how much the speed changed. So I'm going to solve for delta V. Right? This right here would be the area. So I'm going to find the area of this triangle. The area right there would be, that is 20 milliseconds. So 0.02 seconds with a height of 4 newtons. So that is 0.04 kilogram meters per second. And that's all divided by the mass, which is 1 kilogram. And when I divide that stuff out, I end up with 0.04 meters per second. Now remember, this is how much it changed by. Right? So if it changed by that to stop, that means the initial velocity was 0.04 meters per second. Okay? Boom. Because it stopped at 0. that is it.